Everyone. Hello and welcome. So we previously talked about functions, and now we're going to talk a little bit more about some important elements pertaining to functions, and this will help us develop greater things throughout the rest of the course. So we've introduced the ideas of domain and range before. This is where we're going to pick up, and we're going to spend an entire sort of lecture on domain and range and sort of making clear these ideas. Previously, we mentioned that there's going to be some types of restrictions on the numbers that a function can admit as inputs. So, for example, we had the area of a circle. We built a function. A of r equals pi r squared. So this is taking values of the radius, squaring them, and multiplying by a constant, pi, to give us the area of the circle. Well, clearly we can't have circles with a negative radius, and so we had the restriction on values of r that we would allow it as inputs to be positive. So the way to say this is, well, the function is not defined for values of r less than 0, for negative values of negative radii, and the only valid inputs are going to be positive radii. Okay, so this brings us back to some definitions. So suppose we have some q equal to f of t, then the domain of f is the set of all input values t that yield an output value. What does that mean? Well, the domain is the set of all input values t that yield an output value. They're the set of all inputs that we allow to enter this function to return some type of output. The function can be undefined for values outside of the domain, either algebraically or just practically. So in this particular example, the area function's not undefined algebraically for negative radii. So if we had a radius of -2, we could plug this into our formula. It's going to be positive 4 times pi. But we understand that the practical interpretation of a circle with a radius -2 is not a circle of area 4, right? And so that's what I mean. You could have a situation where there's algebraically impermissible values that would restrict the domain, or we could restrict the domain based on our common sense notions of what we expect about geometry or money or whatever it might be, or just for the sake of a variety of applications, we might for no other reason than the fact that we want to focus on one particular area, we might restrict our domain to a particular region. So we'll see this in some of the examples here. Anyway, the domain f is the set of input values that we're going to allow to return values of the function. The range of f is the corresponding set of output values q. So the range of f, the range of the function is the set of points that the inputs are being mapped to. Basically, the domain is our set of independent variables. The range is our set of values. No, the domain is our set of values our independent variables can take on, and each independent variable has its own domain. Typically, we speak in one dimension, so we have one x, that's our one independent variable, and there's some domain for x. We could have multiple independent variables. We don't really talk about that in this course. You can, at least in principle, and each of those variables would have their own domains. Then we have a range for the dependent variable. That's a set of values that the dependent variable is allowed to take on. Okay. So for a of r equals pi r squared, the domain is all negative numbers, and the range is all negative numbers. So we allow any non-negative radius to be an input that we're going to map to an output, and we're going to allow any value, any positive value for our output. So we allow all different types of circles. Okay, so here's an example, finding the domain, evaluating expressions. So if f is defined by an algebraic expression, we have no other information. We typically expect the domain just to be all inputs x for which f of x is defined. If there's any restriction, we're going to be told this. So I'll say this is based on the safe assumption that, of course, we're going to avoid any input that leads to dividing by 0 or taking the square root of a negative number. For each of the following, find the domain. What am I saying here? What I'm saying here is when we're trying to figure out what the domain and range of a function is, we are going to assume that we're not going to violate values of laws of algebra. And so we're not going to allow any values that are going to lead to a divide by 0 error, nor are we going to allow any values that are going to make us take the square root of a negative number. And with those two restrictions, we're going to allow any other values for our domain unless we hear otherwise. So basically, when we're trying to find the domains of these examples here, what you're going to do is look for any violations where we could have a divide by 0 or square root of a negative number, and we're going to define the domain as all numbers minus those particular values. Now, if we hear if we have other information, if there's some interpretation overlaid on top of this, like if we're told this is money, for instance, then of course we're not going to allow negative values, because you can't have negative money. Well, you can have negative money, but if we're thinking about in terms of prices, right? And if we're thinking in terms of time, we typically don't allow negative values of time, although depending on the interpretation, maybe it makes sense. So in those situations, we want to overlay a little bit of intuition to help us figure out what the permissible domain would be. Okay, so anyway, so this example here, f of x is equal to 1 over x minus 5. G of x is 1 of x minus 5, square root of 1 minus x, and the square root of x minus 1. All right, so come up with the domain, find the domain for each of these. Okay, you can go ahead and stop the video, and go ahead and return. Well, for the first one, remember what I said, we're going to assume all values are permissible for the domain, except for the ones that will cause a violation of the laws of algebra. So in particular, for this one, the function f of x is equal to 1 divided by the quantity x minus 5. All values of x are permissible with the exception of positive 5. Because 5 minus 5 is 0, we get a divide by 0 error. So we say the domain is all real numbers x, such that x is not equal to 5. All right, so suppose we have g of x, which is 1 over x minus 5. Here the problem occurs where x equals 0. So the domain is going to be all real x's not equal to 0. With h of x, we have to avoid dividing by a negative number, so we need to restrict ourselves to values of x that are going to be smaller than or equal to 1. 1 is legal because 1 minus 1 is 0, square root of 0 is 0, but we can't have anything bigger than 1, because anything bigger than 1, 1.1, 1.05, whatever, it's going to lead to dividing by a negative, or it's going to lead to squaring by a negative. It's taking the square root of a negative number. Okay, k of x, square root of x minus 1, well, in this case, what we need is x minus 1 is positive, meaning the domain must be values of x that are greater than or equal to 1. So 1 is legal because, once again, 1 minus 1 is 0. We can't have anything smaller than 1. Think of like 1/2. 1/2 minus 1 is minus 1/2. Then we have our square root of a negative number problem. So we need to restrict our domain to values that are bigger than 1 in this case. Okay. We can find the range. Well, suppose we have an equation, f of t equals minus 5. This has a solution, or assuming it has a solution, then the number minus 5 is an output value for the function f, right? So what are we doing here? We're saying, let's suppose we have some equation. It's always equal to minus 5. Assuming this thing has a solution, assuming that we're not working with the empty set, assuming that there is a solution, then minus 5 is going to be one output value of that function. Okay, so the range of f is a set of all outputs, so it's a set of numbers, k, for which the equation f of t equals k has some solution. So let's find for the following functions, let's find the range. Okay, so h of x is equal to 3 minus x, f of t is equal to 2t plus 3, and then g of x equals 3. So that's probably the most interesting to me, actually, this last one. All right, stop the video and think about what the range has to be. Well, in each of these cases, we're going to solve h of x equals k, where k is just some arbitrary number. Where's that coming from? Oh, well, f of t is equal to k has a solution. We're going to find a set of numbers k such that this equation has a solution. All right, so we'll set 3 minus x equal to k, solve for x. 3 minus k is x, right? K can be any number, so we know the range is just all real numbers, right? There's no further restrictions on k. Right? We're not going to get a divide by 0 error. We're not going to get a square root of a negative number error. So k can be anything, which means x can be anything. Okay. All right, so f of t is equal to 2t plus 3. This has a solution, k equals 2t plus 3. Okay, solve for t. K minus 3 over 2. Again, doesn't matter. Regardless of the value of k, this thing's going to have solutions. So the range is, again, all real numbers. Right, we don't have a divide by 0 error. We have a fraction, but there's no possible way we're dividing by 0. We're dividing by 2. and we don't have a square root of a negative number. What about this one? G of x equals 3. This tells us the output is 3, no matter what x is. This is the horizontal line at 3. The range is simply the number 3. It tells us all values of x map to 3. So then the range is simply the number 3. It's just 1 point. More generally, if m is not 0, if the slope is not 0, the range of a linear function is just linear function f of t equals b plus mt. It's just going to be the set of all real numbers. If the slope is 0, then the range is going to be that particular value that particular value of the intercept. Okay, visualizing domain and range. So usually we graph functions with x values on the horizontal. Those are the inputs. This is what we mean by domain. We place the y or f of x values on the vertical. Those are the outputs, and that's what we mean by range. So in more precise mathematical terminology, we say the function f maps inputs x into the domain, or in the domain to outputs in the range, f of x. Okay, the function f maps points in the domain to points in the range, to outputs in the range, f of x. So let's think about this function. F of x is equal to the square root of x minus 1 from before. We said the domain was all values of x bigger than 1. What this means is that if we think about visualizing the graph isn't going to have any values x less than 1. And what about the range? Well, looks something like this, right? Remember, the square root of the quantity x minus 1 can be written as that quantity to the 1/2 power. See, the domain is going to not include any values of x smaller than 1. It's going to begin at 1, and it's going to emanate outward. So the range is going to be all positive reals, because this is an increasing function. Okay, so given the graph of the function f, we can find the domain and range. The domain is always going to be whatever is the leftmost and the rightmost points of the graph along the x-axis. You could just, for the domain, we could just use the endpoints. So whatever are the endpoints, those are going to be our leftmost and our rightmost points. For the range is not going to be the range is going to be the high and low points of the graph. It's not going to be the endpoints necessarily of our function. Look, we're not going to take our first value and our last value and make that our range. No, we're going to take our high value and our low value and make that our range. If there happens to be no endpoint, for example, if the graph begins at 1 and continues to infinity, as in this graph, then we just say the domain is all positive reals. Well, all reals bigger than 1 in this case. The range is all positive reals. Sorry. Okay. All right, so remember I was saying we can take a function and we can restrict its domain and range because we want to focus on a particular segment. Suppose we're doing this here. Right, so suppose I've got some function, I decided let's take part of this parabola out and just pay attention to this snippet. Find the domain and range of this function, f. All right, stop the video, write down your domain, write down your range. All right, so the domain from the previous, the function from the previous slide has domain and range. Domain between 10 and 2. Right, domain is x's between 2 and 10 is our domain. And then what's our range? Our range looks like maybe 2.5. Yeah, 2.5 up to about 8. Yep. How about this one? So let g of x is equal to 1 over x minus 2. Find the domain and the range, and then check your answer algebraically. All right, let's first get its graph, and then let's check it algebraically. Okay, so we can generate a graph. First we make a table. So I'm going to take values of x. I'm going to see what values of x, I'm going to see what outputs these values of x get mapped to by the function. We have a point where it's undefined, right? Where x is 2, we get a divide by 0 problem. And with the points, we can go ahead and we can plot the picture, right? It's going to look something like this. Ooh, so that looked a little bit scary. So what's going on? Well, let's look at our algebraic thing first. First off, we have this undefined thing. We know that the function is going to be undefined at 2, so we're going to have an asymptote. Let's think about the range now. This is going to give us a problem with the domain. Let's see if there's a problem with the range. So 1 over x minus 2 is equal to k, solve for x. The range can be anything but 0. So look, we have 1 point in the domain, 2, and 1 point in the range, 0, that the function can't can't occupy. So that's this right here. We deleted 1 point from the domain, 2, and we deleted 1 point from the range, 0. And notice we've got asymptotes. So this function's going to ever increase up to here, but never quite touch x equal 2. And it's going to ever decrease down here, never quite touch x equals 2. And then over here, it's going to ever increase in this direction, never quite touch 0. Ever increase in this direction, never quite touch 0. So those are our 2 points where the function's undefined. 0 and 2. Okay. So here's just some summary relative to this graph. Well, the expression for g of x is undefined when x equals 2 for the divide by 0 problem. This is illustrated graphically with a vertical asymptote at x equals 2. The graph approaches x equals 2 but never realizes a value corresponding to that x. The expression can never take on an output value g of x equals 0. This is illustrated by the horizontal asymptote, y equals 0. The graph approaches y equals 0, but it never quite realizes that value. Okay, so another thing we can do is we can think about determining the domain from the context. If a function is used to model a particular situation, we only allow inputs that make sense. So we only allow negative incomes because you can be in debt, negative wealth because you can be in debt, but we don't typically admit negative prices or negative salary. We don't think of like negative capacity in your gas tank or something like that. But we do allow for negative profits. Right? We don't allow negative prices. We do allow negative profits. Firms can make losses. Okay, so let's think of this example: gasoline. The amount of gasoline G in gallons that a portable electric generator has remaining after running for H hours is given by G equals 0.75 minus 0.3 H. Find the domain of the function. All right, so what values are we going to allow for H? Well, this requires us being a little bit clever. We know for sure we probably don't want H to be negative, right? Because if our function is defined as the amount of gallons that are remaining after running for H hours, we don't want to talk about running for negative H hours, right? So let's go over this more carefully. The expression G makes sense for all values of H, algebraically at least. In the real world, though, it makes sense to allow H only to be positive and to ignore negative hours. It also only makes sense to allow G, the amount of gas remaining, to be positive. It runs out of gas at G equals 0. So the reasonable domain is going to be 0, or H between 0 and 2.5. We allow time 0, but we have open interval at the upper bound. Why? Well, because for hours beyond 2.5, we have a negative quantity of gas. And then what about G? Well, one thing we can do to find the domain, we can reinforce our solution by solving algebraically. G equals 0. When is there 0 left? Remember, G is our amount that's left. When is this equal to 0? We'll solve for the H, 2.5. So the domain must be between 0 and 2.5. Right? What about for our range? Well, the range is going to be values of G that are positive, right? The range is going to be the vertical. We're going to allow the range is going to go in this direction. Our intercept is 0.75, but our range is going to allow positive values. We might actually restrict this. Maybe we restrict this to maybe we restrict our intercept at the time 0 to be the range. Maybe we say the range is just from 0. G is greater than 0 and less than or equal to 0.75. What would be the interpretation then? Well, suppose we only have 3/4 of a gallon in our tank, right? Our tank capacity is 3/4 of a gallon, so that we couldn't have more than 3/4 of a gallon. That would make sense then to have a restriction of 3/4 of a gallon for my range. And then for my domain, this is going the x direction. 2.5 hours is the max, because beyond there, the capacity would be, or the amount left in the tank would be negative. Okay, very good. So let me know if you have questions.